Hey everyone, welcome to Amazon SageMaker AI Science Corner videos, your go-to location for deep data science and large language model content. My name is Pranav Murthy and I'm a senior Gen AI data scientist. I work on the Amazon SageMaker team and I love building intelligent and autonomous systems. So, the question that's on our minds today is, why should we customize large language models? Most open source and even many closed source large language models are trained mainly on data that's available in the public domain, essentially internet scale data set. This means that they excel at general knowledge and common topics, but may not be aware of your proprietary processes, internal data, or even industry specific information, simply because this data was never available publicly to train on during the process. If your use case depends on specialized concepts, like your organization's internal procedures, unique product details, or specific regulatory requirements, off-the-shelf models might miss the mark. They can even provide generic or inaccurate answers when faced with data they haven't seen before. So to reduce hallucination, this is where model customization becomes super crucial. By fine-tuning an LLM with your own domain data, you provide it with the vocabulary, context, and expertise needed to operate effectively in your environment. If your LLM needs to understand business critical information that wasn't part of its original training, customization isn't just helpful, it's often essential. Now, you might be wondering, if LLMs can be customized, how is it different from methods like retrieval augmented generation, or famously known as RAG, or even just prompt engineering? Why can't I just prompt engineer this into the model, which you might already be using in your LLM applications today? Model customization means actually retraining or fine-tuning a model, adjusting its internal weights so that it learns from your specific data or tasks. You can think of this as updating the model's brain, changing its actual understanding and behavior for all future inputs. This process involves modifying the weight matrices deep inside the network, allowing the model to generalize from new patterns it has never seen before. In contrast, RAG and prompt engineering don't alter the model's core at all. With RAG, you're augmenting the model at inference time or at runtime. You dynamically retrieve relevant documents or knowledge from an external database and append it to the prompt. Prompt engineering relies on crafting your questions or instructions in a way that guides the model's response. In both cases, the underlying weights or the knowledge the model draws on are unchanged. You're simply steering the model with extra content, not actually teaching it something new. A practical example of this can be, before customization, even with smart prompt engineering and RAG, if you ask a generic model to summarize the latest SEC filing for Amazon, you might still get a vague or formulaic answer, especially if SEC filings are unfamiliar territory for this model. After customization, with targeted fine-tuning on your domain data, the model can now summarize SEC filings in exactly the format and detail you require. No additional prompting or context required. In short, RAG and prompt engineering are powerful for extending the reach of a model, but only model customization can truly rewire its internal knowledge for your unique use case. Broadly, there are four main strategies for fine-tuning models. You have supervised fine-tuning. You might have heard of terminologies like SFT, PEF, LoRa, spectrum, full fine-tuning. They all most likely fall under the SFT branch of model fine-tuning. Directly teaching the model with labeled output examples, like providing customer support questions and ideal answers or legal contracts and summaries. The second method is preferential fine-tuning. You may have heard of the terms DPO, PPO, GRPO. This effectively implies teaching the model to prefer certain types of outputs over others, often based on user preferences or reward signals. For instance, making a chatbot more polite or helpful based on human feedback. The third method is called continued pre-training. This category of fine-tuning of a model implies that the training of a model happens longer on domain-specific data, such as feeding it more medical textbooks so it becomes more fluent in healthcare terminology. There's no instruction tuning involved necessarily. You just feed it GBs or terabytes of text and allow the model to converge. Then lastly, training from scratch. If you're a foundation model provider like Amazon or Meta, then you try to build your model from scratch using huge amounts of custom data sets. And you may have heard of internet scale data. This is where it comes in. For example, creating new model just for chemical patent analysis requires terabytes of data or trillions of tokens to produce a small or medium-sized model between 1 to 14 billion parameters. In summary, full fine-tuning, continued pre-training, or training from scratch usually require massive amounts of resources and lots of data, but can dramatically change the way a model behaves. Most oftentimes, and most applications, you may have a smaller collection of data sets. So for that, you would likely be using supervised fine-tuning. And along those lines, today, we'll focus on the most popular accessible approach, supervised fine-tuning, and the sub-methods that are available at our disposal to fine-tune a model with limited amount of data sets. SFT is all about collecting instruction response pairs, or question context answer triplets, to teach a model specific skills like drafting insurance codes, or answering domain-specific questions, or reasoning through legal cases. And beyond just copying answers, SFT lets you teach the model how to reason step by step, making it much smarter and more reliable for your chosen domain. One of the ways to generate SFT tuning dataset is through model distillation technique. But now let's jump into reviewing SFT datasets. SFT dataset that we're going to use for today's demo, you can see the format, but largely the format aligns in the messages format, which usually consists of system, user, and assistant keys, representing a given conversation. For SFT training, you provide the system prompt if the model supports it. Some models may not support it. For example, DeepSeek doesn't typically use the system message format. And user input to the model, which contains the actual query, and then you wait for the assistant to respond, which goes into the assistant key. In our earlier distillation example, the assistant response was generated by a larger teacher LLM, letting us transfer the teacher's knowledge to a smaller student model like a Llama 33 billion. Sometimes the assistant row may also contain high-quality human annotations, which is ideally preferred, but is very hard and very expensive to obtain, and that's where model distillation techniques can be very helpful. So now let's take a look at our dataset and see how the example data that we're going to use for our fine-tuning looks like. For this lab, we'll use the FinAI reasoning financial dataset. And quickly reviewing its structure, we chose this data because it helps induce reasoning skills, clearly demonstrating the value of SFT. One clear thing you can see in this experimentation is before fine-tuning, the model might answer without reasoning, while after SFT, it learns to reason step by step, reducing hallucination, which is especially helpful for smaller models working in complex domains. Now let's take a look at what the dataset looks like before we jump into the actual fine-tuning technique. So just taking a look at the dataset, this data is now available on Hugging Face. The data has about 3,500 rows for us to fine-tune, which is a decent sized data set for evaluation of techniques. Now, if you take a look at the data set itself, it consists of 4 columns. You have the open-ended verifiable question, which consists of a simple system prompt at top to follow instructions, actual context, and a placeholder for question with the actual question in there, and a placeholder for answer where it is asking the LLM to respond back. It consists of a distilled output from a larger model, which consists of the reasoning where it's trying to reason to the answer and then finally the response itself. Now, another unique thing about this data set is it has the ground truth data available. So that means the ground truth can be used to validate the efficacy of the model and how well it has learned. It is deterministic in nature. So a question has a deterministic answer. So you can validate whether your model got it right or got it wrong post fine-tuning. Now let's jump back into the notebook itself. So in this notebook, we're going to use the financial reasoning dataset and try to fine-tune a small language model using primarily 2 techniques. We'll use PEF LoRa and we'll use spectrum-based fine-tuning. You'll learn about both of these techniques in a few minutes. But let's just walk through the notebook and prepare the data set. Let's try to organize the data in a way that we can use it to fine-tune the model, regardless of the technique we use. So here's our notebook. This is available on GitHub. So the first thing is we're going to need SageMaker so we can extract data, push data, and then kick off jobs. So fairly simple. We instantiate a new SageMaker session. We grab the role. And now we are ready to prep data for Hugging Face. So we can prep the data so we can kick off training. So the first thing is, as we already saw, this is how the data set looks like. It consists of 3 sections: the user input with the question. It consists of the chain of thought reasoning from an upstream teacher model, and finally the teacher model's response itself. And it has another auxiliary column, ground truth, which is very essential to determine whether the model got the answer right or wrong, and very helpful in model validation. So next we're going to download this data set from Hugging Face and save it to our local disk. But prior to that, before we actually begin to fine-tune a smaller language model, we need to set context. The context here is that, we're providing a system prompt. So Llama models take in system prompts. In our system prompt, all we're saying is, you're a helpful assistant. You are asked a bunch of questions. You need to respond back, but you need to respond back in 2 parts. You need to think through your answer, and finally provide your answer in the answer tag and the thinks in the thinking tag. So we can separate out the reasoning from the final response. So that's how we are going to process our data set. In our process row, we're going to capture the complex chain of thought, the response, and order it all in the messages format. And now we're going to download the data from Hugging Face. We're just going to print the first row in the data set. We have about 3,500 rows within the training sample itself. Now we're going to map the data set. Let's re-execute. Okay, so the mapping was fairly quick. Now we're going to save the data set to JSON format. And we can see that the data set has been stored here. We can take a quick sneak peek at the data, maybe just expand the row. Here we have the data in messages format. The 0 row is the actual system prompt. The row 1 will be the actual user input question along with the context. And finally, you have the response from the model itself that is used as the ground truth for fine-tuning an SFT model. So how do we train this model? There are 2 ways to train a model on SageMaker. Your SageMaker Studio notebook itself can be backed by GPU accelerators. Even though I do have a GPU-backed notebook, I will still use best practices, which is to kick this job off as a training job. Training jobs inside SageMaker are ephemeral jobs where you can offload your scripts and it'll be run in a headless compute. And when it's done, compute will be terminated and you'll only be charged for the time that you run the job itself. So the first thing it needs is the data to be available in S3 for it to download and actually run. So we've already formatted the data in messages format. So now we're going to upload that to S3. SageMaker offers PySDK for Hugging Face trainers that you can use and manage your training, which means that we take care of, the images, etc. And you just have to bring your scripts and specify what version of the container or Hugging Face that you need. Alternatively, you can also build your own containers. In this example, I built my own containers because I needed some additional optimizations, but you can choose to bring your own container strategy and just use Hugging Face's PySDK to kick off the training job. So what it does need at the top is a token, because I'm using Llama 3 to 3 billion model, where I'm trying to induce reasoning through SFT technique. Since Llama 3 billion is a gated model, I am going to need the Hugging Face token. So I'm just going to paste my token in here. And we can kick off heft and QLoRa method with our data in S3. Okay, so right now the training job has been kicked off. It'll take a while, but the training is going to run in the backend. But now let's take a look at what did I just do here. I have an entry point here, but I'm running some sort of a script. Where is that script coming from? And how is fine-tuning actually taking place? So this script is located inside the subdirectory code. So I'm going to open up that code. Here is my QLoRa training script. My QLoRa training script is leveraging Accelerate to distribute training across 8 GPUs and accelerate the training process itself. But the script that's actually defining the logic for training is under fine-tuning LLM QLoRa. So fine-tuning LLM QLoRa, you can walk through the script. It's pretty simple. It has all the necessary arguments that it needs. It takes in the model type, it loads the tokenizer, it loads the model, and then it quantizes the model based on quantization configuration, uses PEFT to do performance efficient fine-tuning. Then we get into some of these. There is another spectrum configuration which we'll touch upon later, and just simply kicks off the training job. The configuration for how the training is actually defined is coming from the recipes. So in this, you don't need to touch the script at all. The way the script is defined, you can just use the exact same configuration and kick off a training job. But where do you define what model or what LoRa rank would you use, what LoRa modules to save, etc.? You can simply define a recipes up top. The recipes contain information around the model that you're trying to fine-tune, the output directory nomenclature, the max sequence length for your training, what data set you'd like to train it on, whether it's directly loaded from Hugging Face, if it's in messages format, or if you'd like to pre-process the data set just like we did in here, whether you'd like to fine-tune the model, load the model and fine-tune it in 8-bit format, or you're okay in bfloat or float16 format. And finally, number of epochs of training that you'd like to run, the training batch size, eval batch size, all the other parameters. There is another very important component, which is observability. So Hugging Face has integrations built in where it can log training output to MLflow or TensorBoard. SageMaker has managed offering for both. So we have SageMaker first party, MLflow for observability and experimentation tracking. So all I need to do is just put in MLflow here. And then I go back to my training script, and then I have to specify what is the tracking URI. So it knows what tracking server to log it at. And that's it. Now you have a training job that's currently running, and I'm going to stop it here because I've already trained a model and the weights are available for me. Now let's actually take a look at what the integrations look like within MLflow. So to get to MLflow, you go back to SageMaker Studio, click on MLflow. You should have a tracking server available. If not, you can just hit create. Few simple steps and you'll have a tracking server up and ready in about 20 to 30 minutes. And it's only a one-time setup process. So I already have a tracking server available. I'm just going to open MLflow. And I logged my experiment under Hugging Face SFD Llama 3.2, right? It's Llama 3.2 instruct tuning. And under this, I have two training jobs. The one I need to focus on right now is the QLoRa. Under this, I have all my parameters and hyperparameters for training defined here. My metrics are automatically logged. My model metrics like my loss curve, my gradient norm, my learning rate, all of those metrics at runtime are continuously logged here. If I had any system metrics which monitored GPU utilization, those would also be logged into this. And finally, if I wanted to log my model itself, my model weights, I can also log as artifacts to the particular run. Great. QLoRa, we understand the method, we understand how it works. Now let's jump into how you would actually do that with Spectrum. Spectrum has one additional step as compared to QLoRa. So Spectrum requires you to download the Spectrum Git code itself. I have already downloaded it. So this is the Git repo, which we'll be using. The Git repo has all the code built in. You just have to do a Git clone on the Spectrum repo, like I have, and run the simple command, which just requires two things. Spectrum requires you to specify the model name, and then what percentage of the model you'd like to fine-tune. So in this case, because I've already analyzed for the 3 billion model, I'm just going to use 1 billion as the target model for now. And so the first thing Spectrum's going to ask you is, hey, we are going to run a signal to noise analysis on the model itself. So a little bit about Spectrum. So Spectrum is a newer, more advanced method. It leverages a technique known as signal to noise analysis to identify which layers within a model are most responsive to new data. You can then fine tune just these layers or high impact layers, often somewhere between 30 and 50% of the model, while leaving the rest untouched. This gives you a balance between efficiency and impact, making it ideal for complex data environments such as multilingual data corpora, medical document classification, or highly imbalanced data sets. So as we kick off the spectrum-based fine-tuning, you first need to analyze which of these layers will yield the maximum return during fine-tuning. So for that, you allow Spectrum to analyze it. So it's going to ask you for a batch size, and I'm going to specify 2 here. So you can see what it's doing right now is it's downloading the model weights if it doesn't exist within local cache. And then it's going to prompt you to select the layers that you'd like to analyze. If you know what layers you'd like to analyze for maximum yield, then you can select just those layers and allow Spectrum to analyze how good those layers perform in terms of SNR metric. If not, you can allow it to just analyze everything and then compute the SNR information on your behalf. So as you can see, it's going layer by layer, analyzing this information. It's a one-time process, and effectively what it does is it dumps a JSON configuration file that Spectrum uses to then either freeze or unfreeze layers based on the SNR analysis. So as you can see, it has dumped a signal to noise YAML file here. So let's just take a quick sneak peek at the YAML file. So according to Spectrum, these are all the layers that will yield the highest result when fine-tuned using Hugging Face Trainer. But why these layers? There's another JSON here that is available. So if you take a look at maybe model layer 0, input layer none. So if you go down to the particular layer, you'll be able to understand what the SNR calculation is. And then you can work backwards as to why those layers were specifically chosen for fine-tuning. That's it. It's a one-time task. If you rerun it again, it's going to use the cached information. This is all you need. Now, when I go back into my code base, the same code base that we have, it's almost identical. It's called fine-tune LLM Spectrum. Now, it is looking for a Spectrum config. That's the additional component. So in the Spectrum config file, we placed for the particular model. In this example, we're using 3 to 3 billion with 50% unfrozen layers. So SNR has been analyzed for 50% of the model. And we're trying to fine-tune the most impactful layers from there. Now let's get into the recipes. I've created a new recipe file. So now that I have my Spectrum and I have my recipes file, I just specify the Spectrum config path right here. If I need to load it in 8-bit or 4-bit, I can do that just to save more resources. But I'm not going to do that in here. I just provide my Spectrum configuration, specify the number of training epochs, exactly the same configuration as before, and I'm going to log all these metrics to MLflow. That's it. So now let's jump back into the notebook. Now that we've run the Spectrum analysis on Llama 3 to 3 billion model, now we can just kick off a training job. That is it. It's as simple as that. Now, obviously, training job takes time. For the purposes of this demo, I had fine-tuned a model ahead of time. So let's take a look at qualitatively and quantitatively the difference between fine-tuning using PEFLORA versus fine-tuning using Spectrum on the exact same data set with identical configurations. So if I go back to MLflow, as you may have observed, there are 2 runs present here. The first is the QLoRa run at the bottom, and then you have the Spectrum run up top. Both of these were approximately trained for almost the same duration of time. So what I'm going to do is select both and then compare the runs. So in here, you'll be able to compare what changed between one run versus the other, what were the parameters, what were the metrics, etc. So as you can see, all of these values, the diff values between the two runs. But what is really important is overlaying the graphs between the two runs. So as we overlay, you can see that the runs are almost identical. The gradient norm has some variation, but the important observation to be made here is the loss curves. Now, if you observe the loss curves, the pink loss curve is from Spectrum, whereas the green loss curve is from QLoRa. And both of these loss curves are for 10 epochs for the same data set, trained for the similar duration of time. Now, a key thing to observe here is, as you can see, as you open up more layers for fine-tuning, you can see the loss has dropped. And both of these have been trained on similar kinds of instances. So Spectrum takes a little more resource than QLoRa, but you can almost see that the Spectrum fine-tuning method has converged faster with similar number of steps, like it's step number 205. The loss for Spectrum is much lower than the loss for QLoRa. Now, what does it tell me in simplistic terms? What it tells me is, if you use Spectrum and your data distribution is more complex, you'll probably reach convergence faster with Spectrum than you did with PEFT QLoRa. But, however, if your data set is simple enough, you may be able to get away with just running or fine-tuning a QLoRa adapter rather than going for complex Spectrum fine-tuning. However, through the demo, what I wanted to highlight is it's a one-time simple process of generating the configuration file, and then you can decide how you want to mix and match the data set and the models in order to fine-tune it. Okay, now we know we went deep into Spectrum-based fine-tuning, QLoRa-based fine-tuning. What we didn't dive into is full fine-tuning, hopefully in an upcoming video. But for now, let's take a step back and summarize our learnings. There are three dimensions along which we need to analyze what we've just done. Memory and compute, which is essentially resources. Expressivity and adaptability, which means how well is a model able to understand nuances within the text itself, and what kind of situations is it best for. PEFT and QLoRa, as you know, uses the lowest amount of memory and compute, has medium level of expressibility and adaptability. As your data sets get more and more complex, QLoRa can tend to be less and less efficient. So QLoRa or PEFT methods are great for rapid adaptations or domain transfers and memory limited scenarios. So if your data set is simple, if you've only got one GPU, QLoRa and PEFT is the way to go. Spectrum fine-tuning has medium amount of memory and compute required, so lowest low. Expressibility is higher than QLoRa, which means it'll be able to understand complex tasks, multilingual tasks, better for inducing reasoning capabilities in smaller models, and obviously is more tuned for wide array of use cases that needs to be broadly domain aligned. Next, we get to full fine-tuning. If you remove Spectrum and PEFT-based methods, what you end up with is full fine-tuning. That requires the highest amount of memory and compute, has the highest level of expressibility and adaptability, which means that it basically got all the weights at your disposal to tune. There are certain risks you need to take into account, but outside of that, you get the maximal performance. You need high amount of compute budget, and these I would recommend limiting it to tasks that are super complex, where you're using full fine-tuning to fine-tune medium-sized models distilled from super large models like Scouts or Maverick, for example. Outside of that, thank you so much.